Hello students, welcome to the lecture video of DCMT, DC Machines and Transformer. So this is the first video for this course. Already in the offline, we have started with the introduction about the course. The module 1 is about DC machines, in that the first topic is DC generator. Very first thing, we must know what is an electrical machine. It is a two-port device, and the electrical machine is an electromechanical energy conversion device. Means that the generator, motor, analog instruments and actuators all comes under electrical machines. Electrical machine is a continuous energy conversion. It has some input and there will be an output. In between there is a conversion takes place, that is by means of electrical machines. Yes, electrical machines can be classified into generator and motor. Very simple, the generator which converts the mechanical energy into electrical energy, whereas motors that converts electrical energy to mechanical energy, meaning that generators will have the mechanical input, electrical energy as output, electrical energy as output. For motors, we are giving the electricity to the motors. Electrical energy is the input and it rotates. The rotation, mechanical energy will be the output. Basic classification of electrical machines, generators and motors. And you know very well that we have DC system and AC system, direct current and alternate current. If my machine is dealing with AC, if it generates the AC electricity, it is AC generator alternator. Or if it requires AC supply for mechanical output, that is motors which requires AC supply, are called AC machine, AC motors. Similar thing, the DC machine is there, meaning that if your output of generator is DC supply, then it is DC generator. And if you have a motor which requires a DC supply system, direct current supply, then it is DC motor. So machines will be of AC and DC, that is based on the nature of supply generated or nature of supply given. If it is a motor, we are giving the supply, that can be AC or DC. If it is AC, it is AC motor. If it is DC, then it is DC motor. And if it is a generator, it is generating the electricity. The generated electricity is AC, alternating current, then it is called AC machine, AC generators, alternators, synchronous generators. And if we are generating the DC supply, it will be DC generator. Our point of interest here is DC machines, since the course is DC machines and transformers, right? So in DC machines, it can be a motor or generator. If the input is electrical, output is mechanical, it is motor. If the input is mechanical and output is electrical, it is generator. So in general, we are denoting DC machine. It meant for motor or generator. So the DC machine can be classified into two different types based on the excitation, self-excited and separately excited. Excitation meaning that exciting the field winding, magnetizing the field winding, magnetizing the coil, exciting the coil, giving supply to the coil producing magnetism inside the machine is called excitation. It can be done as self excitation or separate excitation. In detail, we will discuss later. Now, you just know there are two different types. One is self excited, another one is separately excited. Sub-classification of self-excited will be three different classification series: shunt, compound, and the compound type can again classify to cumulative, differential, and these two are again classified to long shunt, short shunt, long shunt, short shunt. Again, more discussion on all these types will be done later, since we are going to study in depth about all these things. So in general, the applications of electrical machines are listed here, and also in the offline class, you guys have listed a lot of applications. Yes, the principle of electromechanical energy conversion is a reversible process. That is, the conversion of energy from one form to another is possible through the coupling field. Usually, the electrical energy will be converted to mechanical or vice versa, mechanical to electrical or electrical to mechanical. Both conversion takes place via a medium which is called the coupling field. The coupling field can be of electric or magnetic field. The conversion of electrical to mechanical or mechanical to electrical both can happen through a coupling field. The coupling field can be electrical or magnetic. Most of the cases it is magnetic field. Yes, the field system, this armature system in magnetic field, that is the coupling field is magnetic field. We require two different systems, that is field system and armature. So field system in DC motor we call it as the stator. This is stationary, so we call it as stator. And armature system in DC machine we name it as rotor, the rotating part. Armature system is rotating, field system is stationary. When you go to AC machine, that is synchronous machine, the field system is rotating, armature system is stationary. So the armature and field system can be of stationary or rotating. That is based on the DC or AC machine. Yeah, here we have the block diagram which shows the flow of energy in electromechanical devices. It is for motor and generator. Here the electrical source, mechanical sink, meaning that electrical to mechanical. This is motor, and we know very well there should be some coupling field between electrical to mechanical. Similarly, electrical sink, mechanical source, so the input mechanical, output electrical. This is generator. Here again we require a coupling field which converts the mechanical to electrical. So in between electrical to mechanical, there are a lot of losses takes place. The input what we are giving is the cross electrical input, and we have some ohmic losses and iron losses, and net electrical input is converting to magnetic field, and after converting into magnetic field we have losses associated with mechanical, so that we will get the net mechanical output, and finally at the end in the shaft we will get the final mechanical output. So like that, when it is mechanical input, cross mechanical input will be lost some amount of gross mechanical input will be lost due to mechanical losses, that is rotational losses, and it is converted to magnetic field. After getting converted into magnetic field, there will be losses associated with the electrical side, that is electrical losses. So finally you will get the net electrical output. This indicates that in both the conversion there are different losses associated in electrical and mechanical. Yeah, here it is explained, that is electrical energy input is equal to mechanical energy output plus energy stored in the coupling field plus energy losses. When you see it for generator, you know mechanical energy input is equal to electrical energy output plus energy stored in the coupling field and losses. So whatever input we are giving, some part of the input will be taken as output and some part of the input is lost due to various reasons, and also in the motoring action as well, the electrical input, mechanical output. So with this we know the efficiency calculations. We are calculating efficiency, right? Efficiency usually it is output by input. That is actually less than 100. It will be given in percentage, right? So we are getting less than 100 always, right? There is no 100% efficient system, meaning that the output is lesser than the input. There will be losses. The energy losses are ohmic losses, core losses, mechanical losses, different losses associated. Again, this topic we will have a discussion after completing the construction, principle of operation, all those things. Coming to the basic concept, you know, the basic concept of DC machine will require different laws and rules. In that, Maxwell's corkscrew rule is one important rule will be used in DC machines. These are all the things you might have studied in your schoolings. You just recollect all those things. Corkscrew rule says that see the direction of magnetic field and the direction of current, the direction of rotation. So it shows the direction of rotation, direction of magnetic field, and the direction of current. Current, magnetic field, and rotation. So the force direction, current direction. Fleming's left-hand rule, or also called motor rule. Fleming's right-hand rule will be used for generators. In your left hand, if you position these three fingers perpendicular to each other, that indicates the thumb movement. Thumb is for movement, the rotation, and the forefinger is for the field, and the second finger is for the current direction. So if you know the current direction and the field direction, you can find the motor rotation, movement of motor. So like that, the Fleming's right hand rule will be applied for generators, electromagnetic induction. Faraday shows that electric current could be produced by the movement of magnetic flux related to the coil. He also showed that the magnitude of EMF induced is proportional to the change of flux. Here we have a coil connected with a battery, and when you excite this coil, you get the magnetic flux that will generate, if the coil is moving, that will generate electric current. So for explaining that, we have this the movement of magnet. This coil is connected with generator. So Faraday's law of electromagnetic induction. It has two laws. One is the first law, that is, whenever a conductor cuts the line of magnetic flux, an EMF is induced in it. The second law states that to find out the magnitude of induced EMF, we apply the second law. The magnitude of induced EMF is proportional to the rate of change of flux. Rate of change of flux, that is given as an equation, that is E is equal to minus n into d pi by dt, where E is induced EMF, n is the number of turns in the coil, d pi by dt is the rate of change of flux. And it is minus. Minus indicates that induced EMF has a tendency to decrease the change of flux. Just already told you that. RHR, generator rule, Fleming's right hand rule. So in your right hand, if you keep these three fingers perpendicular to each other, this thumb indicates the motion, and the forefinger indicates the magnetic field direction, and the second finger indicates the EMF. And we also apply the Lenz's law. Direction of induced EMF in a coil is such that it opposes the cause of production. Lenz's law states that direction of induced EMF in a coil is up is opposite to the cause of production. So by applying these things, we can find out the basic principle of magnetic field. A current carrying conductor wire produces a magnetic field in the area around it. If it is generating action, moving wire in the presence of the magnetic field has a voltage. In a motor case, a current carrying conductor wire in the presence of magnetic field will experience a force. And in transformer, a time changing magnetic field induces a voltage in a coil of wire if it passes through that coil. DC machines can act as a generator or motor. Construction wise, it is same. If you give mechanical input, it acts as a generator. If you give electrical input, it works as motor. Coming to the constructional features of DC machine, it has a stator and rotor. See the stator, and this is what the construction diagram of DC machine, which is a cross-section view, which has a lot of parts. Better you can draw this diagram in your notebook so that we will have a discussion about this. What are all the parts available? What is the purpose and function of each part? How those parts are made? So like that we will have some discussion on that. You just copy this in your notebook. Thank you.